This slideshow will explain the process of liquefaction in a little more detail than is presented in your textbook. Liquefaction is one of the primary causes of building collapse during many earthquakes. Liquefaction only occurs in sediment that is saturated with water. The water table is high, and the base of any structures built on the ground are in contact with both the sediment and the water. There are three key forces or stresses that are important in liquefaction. The first is the weight of the structure, which presses down onto the ground. This weight is balanced by two upward-directed stresses. The first upward-directed stress is transmitted by the sediment grains themselves. It is carried by the grain-to-grain contacts between the grains and is called the effective stress. The grain-to-grain stresses are shown as white arrows, and the upward-directed effective stress is the brown arrow. The second upward-directed stress is transmitted by the water through the water pressure. It is shown by the blue arrow. These three forces or stresses are related to each other by the laws of physics, which state that the sum of the forces must be zero, or else the structure will move. This means the downward push of the structure's weight must exactly balance the upward push of the effective stress plus water pressure. This relationship is expressed in the language of math as the effective stress equation, shown here. Traditionally, stresses are given the Greek symbol sigma in physics, and the effective stress is distinguished from the load stress with a little bar over the top. During an earthquake, the seismic waves cause the ground to shake or vibrate. When they're vibrating, the sediment grains can't push as hard against each other, and the effective stress decreases. According to the effective stress equation, the water pressure must increase to compensate. Click on the figure to see an enlarged, slow-motion animation of what this looks like. The water pressure is indicated by the height of the blue bar. Notice how it shoots up as the effective stress decreases and the water pressure increases. This animation will show you how the effective stress equation changes during an earthquake. Since the weight of the structure doesn't change, the total stress remains constant. However, the shaking causes the effective stress to decrease and thus the water pressure to increase. Click on the blue button to see. If the shaking is severe, the grains can lose all contact with each other, causing the effective stress to drop to zero. At this point, the entire load of the structure is being borne by the water alone. It's as if the building were sitting in a lake instead of on the ground. What happens next is entirely predictable. The building begins to sink into the fluid. It will continue to do this as long as the shaking keeps the sediment grains apart. Click on the image to see a simulation of what happens to structures when the ground beneath them experiences liquefaction. Liquefaction is more than a theory suggested by laboratory experiments. For example, this incredible aerial view of Niigata, Japan, after the severe 1964 earthquake, shows the effects of liquefaction on a series of apartment buildings which toppled just like the toy in the experiment. Evidence for liquefaction is sometimes found in piles of sand or other sediment on the surface following an earthquake, such as this example from California. The sand is carried up by water when its pressure increases during liquefaction.